and good day to our audience. Dan and I are going to spend the next 45 minutes with you, and we're going to introduce you to an advanced material which we believe will be very helpful in solving thermal management problems, and also introduce you to a new modeling tool that will be available to audience members at the end of our presentation. So our topic today is thermal management. And of course, those of you in the audience realize that thermal management has become a bigger and bigger issue due to the increasing requirements for increasing power in semiconductors. And the issue poses itself in many ways, but a general rule of thumb is that the lifespan of semiconductor devices is halved for every 10-degree rise in junction temperature. There are many solutions available today, and some of them are posed for solutions of tomorrow, one of which would be carbon nanotubes, which is a very exciting development, but unfortunately, that one is largely in the academic realm. It could be the thermal management material for the next century. But what we're going to talk about today is a material that is available and has been available commercially for the last 50 years. But it's one that is not very well understood by the thermal management community. We are located in Easton, Pennsylvania, and the company that we represent, Mintech International, is the world's largest supplier of high-purity pyrolytic graphite. And pyrolytic graphite is going to be the main topic of the advanced material for today. And it is the thermal management material of today. One way you can think of pyrolytic graphite is as a three-dimensional graphene. Graphene, of course, has been in the news lately and was the recipient of the Nobel Prize. You can think of graphene as a single layer of graphite. Pyrolytic graphite is produced via a chemical vapor deposition process where we grow on a substrate continuous layers with a hexagonal structure, very strong covalent bonds that give extremely good thermal and electrical conductivity in the plane. However, this material is rather unique in that it is highly anisotropic. And anisotropy means that the physical properties are not the same in all three directions. And you can understand that with the diagram at the bottom of the page, and think of pyrolytic graphite as being built up layer by layer in a three-dimensional structure where there is extremely strong covalent bonding in plane, but only weak van der Waals forces between the planes as it builds. So one of the important takeaways for this material is that when you think of graphite, not all graphites are the same. And in fact, we are all very familiar with natural graphite. Natural graphite is inhomogeneous. It has a limited columnar structure. There's many dislocations and point defects. But pyrolytic graphite, and our trade name, by the way, is Pyroid. So you see Pyroid HT. That is a synthetic pyrolytic graphite with high thermal characteristics. This material is quite different than natural graphite. It has a polycrystalline structure. It's got extremely high purity, over 5 nines pure, no point defects. It's got a columnar structure. It's highly oriented. We can do an X-ray diffraction, and you get a very clean pattern. It approaches the theoretical density of carbon. And it's lightweight, therefore, 2.25 grams per cc, with very limited, if not zero, porosity. To summarize some of the benefits of Pyroid HT pyrolytic graphite, this slide gives a brief summary of some of the key features. First of all, we have high thermal conductivity, but that high thermal conductivity is expressed in only two directions. That conductivity has been measured via laser flash diffusivity at 1700 watts per meter K. The two directions that you want can be your choice, but because of the anisotropy, it is two directions. Lightweight density, it has a CTE that is lower than most of the alternative materials and is a closer match, therefore, to power devices. It can be tailored in thickness or shape, and because of that lower density, it is easily cut, diced, or lapped in a variety of machining operations. One important feature that we'll talk about next is that it also can be metallized, and that, of course, is key when you want to attach it to an electronic device. What the customer sees is significant thermal management spreading, a very fast and uniform thermal response, the weight savings of a lower density material, the ability to directly solder an attachment, increased component reliability, and lowered system costs. One of the key technical advances that enabled this technology and this material was our development of metallized coatings that can be attached directly to the pyrolytic graphite. We can do this in a variety of methods, electrolysis, electrolytic, or sputtering coating processes. And we can do this in very thin and, if necessary, multiple layers of electronic-grade coatings. Some of the materials that we have tested as a system could be titanium, nickel chrome, gold, platinum, copper, copper gold, nickel, or nickel chrome. In fact, to date, we have responded to customer requests, and we have not yet seen a metallic system that we have not been able to utilize in our applications. We've done Sebastian pull testing that has yielded results that show that the attachment is of a nature that is suitable for electronics systems. Now I'd like to go through one example of a case study which demonstrates the powerful ability of Pyroid HT pyrolytic graphite to remove heat from a source, point source, which we will use as a laser diode. So this schematic, which was generated through finite element analysis, has as an input a laser diode with a constant heat flux of 200 watts per square centimeter. Below it is attached Pyroid HT, in which the high conductivity directions have been chosen to be through and across one of the planes. The heat sink is made up of copper and is kept at a temperature of 30 degrees C. And the challenge that we want to explore is how does, under these conditions, Pyroid HT pyrolytic graphite compare to other more conventional current alternatives. This schematic demonstrates the difference in heat spreading capability for Pyroid HT pyrolytic graphite on the right-hand side with a thermal conductivity of 1700 watts per meter K versus a copper molybdenum with a thermal conductivity of only 160 watts per meter K. And notice that not only is the junction temperature underneath the laser diode much cooler in the case of the Pyroid HT, but it's also much more uniform across the body. One of the ways I like to express its ability is almost like a thermal superhighway for removing heat and delivering it to an attendant heat sink. We take a closer look at the results in the junction temperature. What we see is as much as a 70 degrees C reduction in that junction temperature compared to copper molybdenum, and yet a very substantial decrease in junction temperature if we compare to copper. I have done this presentation at various IMAPS conferences in the last few years, and without fail, this is something which is of great interest to attendees who are charged with taking care of thermal management problems. We mentioned at the beginning of the presentation that 10 degrees C is seen as something rather significant. Well, 70 degrees C certainly opens a lot of eyes. But there's two ways we can also look at this ability to lower junction temperature. One of which is to lower that junction temperature, thereby increasing the life of the device. But a second and equally interesting way is to maintain a junction temperature while increasing the power output. And that really is something that customers around the world are exploring more and more, again, in keeping with the theme of increasing electronic power output and increasing thermal load. So while we've talked about the thermal management characteristics of Pyroid HT pyrolytic graphite, I also like to leave you with a couple of other physical properties that is very important for the lifetime of this product and its ability to be utilized in severe thermal cycling applications. And that first property that we would like to discuss is the modulus of elasticity. And what we see in its modulus of elasticity, it is quite lower than some of the alternatives, including diamond and copper. And this becomes important. If you think of thermal cycling, the ability of thermal management materials to perform has a lot to do with the ability to conform to the surface to which they are attached. The modulus of elasticity of Pyroid HT pyrolytic graphite enhances its ability to conform under severe thermal cycling operations. We use, finally, that modulus of elasticity to look at the difference in stress that is encountered when using pyrolytic graphite Pyroid HT combined with a common silicon versus either diamond or copper. And simply using the textbook calculations, what you find is that the pyrolytic graphite Pyroid HT yields an order of magnitude lower thermal stress than alternative materials. We believe this also plays a role in its advantage and design characteristics. So that's a very quick introduction to Pyroid HT pyrolytic graphite. It has the ability not only to have that high thermal conductivity of 1700 watts per meter K, but also has the advantage of weighing 75% less than copper. So we'd like to spend the next phase of our presentation by reviewing some of the thermal performance that is evidenced through a model. So I'd like to turn over the program now to Professor Sabatino of Lafayette College, who will discuss the thermal performance model that you can use to see how Pyroid HT pyrolytic graphite can benefit your design of heat sinks and heat spreaders. Dan?
Thanks, Bob. So I'm going to first introduce you to the modeling techniques that we used before we show you how you might be able to use these models to do some first-order estimates for how Pyroid HT might perform in your applications. So we took two approaches. The first approach was to provide a simple model for the performance of a finned heat sink. And the idea was to use a model that would be able to generate results very quickly so you could explore the design space that you're considering. So the approach we used was to take a heat sink where it was assumed that the heat load was the same size as the heat sink as shown in the diagram, and that the high conductivity directions of the Pyroid HT would be along the fin direction and along the width as shown in the diagram. To do the model, we took a simple approach of using a theoretical performance model and looked at each fin individually. So the model is represents the conduction and the convection through the base element, and the conduction and the convection through the fin element. And then we simply replicate that analysis for however many fins are selected. This, again, is a first-order model that helps identify conditions that might have large benefits, and then it would be assumed that more detailed analysis would be required to find a specific performance prediction. The other model that you'll have available to you handles the case of a flat plate heat sink, or a via. So in this case, the user has the option to select a heat load that might be the same size as the via, or it could be a different size in this case, where there's some kind of fluid flow, air or liquid, across one side of the heat sink. And you'll see in the model, you'll have the choice of putting the heat load on the same side or on the opposite side of the fluid. But to handle this kind of problem required a little more complex modeling. So in this case, we're using a finite difference model where we break the heat sink up into elements, orthogonal elements, and we use that mesh to calculate the conduction through the material. The details about this modeling and the assumptions and the theory are contained in a paper that was published in 2014, which you can find online. In the paper, we explored generic situations and tried to provide generic directions of where the Pyroid HT might be beneficial. The idea of the tool that I'm about to demonstrate allows you to make those comparisons more specific. So if you give me a moment, I'm going to share my screen with you, and I'll do a live demonstration of the tool. What you should see on your screens now is the interface for the finned heat sink model. And bear with me as I walk you through the interface and then show you some example calculations. Generally, the interface is laid out left to right, that the yellow highlighted areas are inputs from the user, and moving to the right, those are outputs from the tool to give the user feedback. Let's start in the top left corner which is identified as the design parameters. Here we have an H value, which I'll discuss in a minute, and then maybe more familiar geometric parameters such as the fin height, the fin thickness, and the heat sink length. In each of these boxes, there's a question mark to allow the user to get context-sensitive help. I'm going to click over here on the geometry model because in there is a window that will help me understand what these parameters mean. So the fin height is the height from the base to the tip of the fin thickness being in the transverse direction, and heat sink length as shown in the diagram. I have the ability to enter those values, any value I'd like, and the units are listed here in millimeters. But the idea of using these first-order models was that it would give you the ability to look at a wide range of conditions around your design condition. So besides the specific design condition, you're also able to enter a range by indicating the low and high value of the range. So in the case of the fin height, we have selected the low value to be the same as design at 75 millimeters, and the high value to be 100 millimeters. But you also have the option to enter this as a percentage instead of an absolute value. So if you look at fin thickness, the design is selected to be 2 millimeters, but we've selected a range we'd like to consider between 90% of that and 110% of that. So you have the option to enter it either way. Simply by including the percent sign, the code recognizes your intent. Now let's revisit the first parameter, which is the H parameter. The H parameter represents the convective heat transfer coefficient, which is a model of how well the fluid, whether it be air or a liquid, can remove heat from the heat sink. This is given in watts per meter squared Kelvin. However, I know that most designers don't typically work with H directly. So we've included a simple calculator that you can access through this calc button that allows you to estimate a reasonable heat transfer coefficient for your conditions. What you need is a flow distance, the length the flow will travel, and a flow velocity. In our case, we've recognized that the flow would travel through the heat sink along the fins. So the heat sink length is the flow distance in our case, and the tool automatically delivers whatever heat sink length you had selected in the design conditions to here, although you're free to change that here if you like. The flow velocity is the user's choice in millimeters per second. You can select a cooling fluid for now. It's just air or water, but we can certainly add any fluid that someone needed. And then whatever the temperature is you expect for the cooling fluid. And at the bottom, it outputs an estimated heat transfer coefficient. In our case, the tool we have listed at about a 10 watt per meter squared Kelvin. H is what we think we might have. So we could use the tool this calculator to identify what would take to achieve that, and that would be about 300 millimeters per second, and a 50 millimeter heat sink length would give us about 10 watts per meter K. So we'll close that tool out, and we can see again that for the heat transfer coefficient, we've selected a range we'd like to consider between 90% and 100% of the design condition. I'll come back to these Y and X axis features in a moment, but let me continue with the rest of the inputs down the left side. The other geometry inputs that the user has available to them is the number of fins. So you basically select the overall size of the heat sink by selecting the number of fins. We can change the size. If I select 10, you'll see the representation in the geometry window change. And if we go back to 20, you'll see that the geometry model is updating live to give you a sense of the aspect ratios and the overall size of the heat sink. The gap to fin ratio, I'll demonstrate by going back to the help over here in the geometry model and show you that that's how you dictate the gap between the fins compared to the fin thickness itself. So a selection of 100, the space is the exact same size as the fin thickness. If I make that 500 just to illustrate, then the gap becomes 5 times the fin thickness. We'll go back to 100 because that's more reasonable for a typical heat sink. The base thickness represents the thickness below the fin, so if I accentuate that by making it much larger, let's call it 15, you can see the thickness of the base increases as well. So we'll return to 5. And the heat sink width, which is the overall width in the other direction, I'll show you that again. In this direction, that's calculated from your parameters. The real value of the tool is that it doesn't just give you the performance of the Pyroid HT, but it allows you to show that in comparison to a material of your choice. The choices built in right now are aluminum 6063, just because it's a high thermal conductivity aluminum, and copper, but you also have the ability to enter any custom thermal conductivity you would like. For today's demonstration, we'll just compare it to aluminum because it's a common choice. And finally, at the bottom, the conditions you enter refer to the heat load conditions. So in this case, we're considering a heat load of 100 watts, and the ambient conditions are at 22 degrees C. I've already alluded to the geometry model in the middle. This is just a graphical representation of the heat sink so you can get an idea of the reasonableness of your selections. And it's just showing you the design conditions. But you can change the orientation if you like and zoom in to see the spacing more clearly. But it just helps you understand the design that you're currently considering. Now let's talk about the numerical output. On the upper right is a graphical display. And let's just take a minute to walk through this step by step. The yellow is representing the comparison material. In this case, this is aluminum. The blue is representing the Pyroid HT performance. The y-axis is representing the junction temperature in degrees C. The x-axis is selectable by the user. So in this case, it is the fin height. And that was selected back here in the design parameters area where there's an x-axis selection, and it's currently selected on fin height. So what that is doing is plotting the performance for all the fin heights as defined by the low and high value in design parameters. So we can see we selected 75 and 100, and on the x-axis over here, it goes from 75 to 100 millimeters. The solid line, as indicated by the T or the legend, is the performance at design conditions. So exactly for the column here of an H of 10 watts per meter squared K, 75 millimeter fin height, 2 millimeter fin thickness, and 50 millimeter heat sink length. And so already you can see that there is a performance benefit in this case for the Pyroid HT because the aluminum is here above the blue line, which is the Pyroid HT. But also represented besides the solid line are dashed lines. And again, the legend reveals that the one dashed line refers to the high and the other dash refers to the low. And that again refers to this range in the design parameters. And this box here, which indicates y-axis, tells me which design parameter I'm varying. So we have the fin thickness selected as the y-axis variation, and it's between 90% and 110% of design. So this vertical range here represents a fin thickness change between 90 and 110% of the fin thickness. But notice that the high is actually a thicker fin is actually reducing the temperature. So the high thickness value gives you a lower junction temperature, and the low thickness value gives you a higher junction temperature. One of the things that can be revealed is that the aluminum in this case is more sensitive to a change in fin thickness than the Pyroid HT is by the size of those bands. Let's consider Oh, I apologize. One more thing to point out, that the design performance is indicated in the bottom right. So this is the specific values of the junction temperature for the aluminum and the Pyroid HT, as well as the calculated heat flux for your specific design conditions. If you wanted to simply look at one of the materials at a time, this button toggle comparison allows you to show just the aluminum if you like, just the Pyroid, or together. So let's consider a little more challenging case and see how the tool helps you see the performance difference. I'm going to increase the fin range a little bit by changing the fin height to about 100. I'm going to start with a slightly thicker fin and a longer heat sink. So I've just changed our design parameters, and you can see that the geometry model shows the change in the geometry. I'm going to also make the problem a bit more challenging by increasing the heat load to 200 watts. And so in this case, design is represented on the graph by the 100 millimeter fin height, which is the left of our graph. But we can see, because we're looking at a range of fin heights, that we would expect the performance to improve if we had a longer fin, because the Pyroid HT is able to conduct that heat through the fins better and have the fluid remove it more effectively. And in this case, this provides us a temperature difference of about 3 degrees C. But if the problem is a bit more challenging, let's say, for example, we don't have that much room and we have to make the fins thinner to fit the package. Let's talk about a case where the fin thickness is 3 millimeters. Oh, I missed a parameter on that last one. I apologize. Let me step back 1 second. Let me start with a smaller heat sink at about 10 fins. And now what we see is a target temperature, junction temperature, about 110 degrees C, and that gives us about a performance benefit of about 6 degrees for our first case. Now let's make the problem a bit more challenging and reduce the fin thickness to 3. That's going to increase our junction temperatures for both the aluminum and the Pyroid HT. So if we want to maintain about 110 degrees C at the junction temperature, we're going to have to increase the fin count. Let's just go up by 1. Now we've met what is our design parameter of about 110 degrees C. So the design performance to the right shows a Pyroid performance of 105. But actually the benefit is increased. In this case, by reducing the package size, we've not only increased the temperature of the aluminum, we've actually reduced the temperature of the Pyroid. So the Pyroid benefit is larger. Let's make the problem even more challenging. Let's say that because the fins have gotten closer together, because we needed a smaller package, we weren't able to move as much air through the fins. Let's represent that challenge by reducing the thermal heat transfer coefficient, H, to 5. And now we can see again that if we simply reduce that airflow, the Pyroid HT and the aluminum both have very high temperatures. So let's modify the design a little bit more. And we know from looking at the chart that we will get better performance at higher fin heights. So let's increase the fin height to 150. Let's say that our package has to be even tighter, so let's go to 2. We're still not making our performance, so let's increase the fin count to about 15. So what we see here is now a very small package operating under much more difficult conditions than we started with, relatively low airflow, relatively thin fins with tight spacing. But the Pyroid HT is basically able to manage to achieve the same performance, but the aluminum performance would have deteriorated quite a bit. So in the beginning, where we were showing a 6-degree performance benefit, this is about a 15-degree performance benefit. It illustrates the design space where the Pyroid HT shows the most benefit, which is the most challenging conditions, where you have a small package and you have relatively low airflow rates. Now, besides the thinned heat sink model, which I've been showing you, there is another tool to handle the flat plate model. I won't go through it in as much detail, but I'll introduce it because it has a very similar interface. So this is the flat plate model, and it has a very similar layout, that the inputs are on the left and highlighted in yellow, and the outputs in blue are to the right. You have a very similar set of inputs, although the geometry is slightly different. So in this case, you're again selecting a heat transfer coefficient H, but now what you have is a selection of both the heat source and the heat sink size. So this handles square geometries, and you can select the heat source length in millimeters, and then the ratio of the heat sink to the heat source, as well as the plate thickness, that is the heat sink plate. That's represented down in the temperature distribution graph down below to the right, where the white line in the middle is representing the size of the heat source, and the color contours are representing both the size of the heat sink as well as the temperature distribution across it. And in this case, you can see that the aluminum temperature distribution can be seen as going from about 55 degrees to 51 degrees, whereas the Pyroid HT is almost completely uniform in temperature at about 51 degrees, and really illustrates the benefit of the high thermal conductivity. You have several other options in this case. You can choose the arrangement of the heat source and the cooling flow. So the geometry block allows you to select a case where the source is on the opposite side of the cooling flow, or in the picture below, where the source and the cooling flow are both on the same side. You can change the orientation in this case of the high thermal conductivity direction of the Pyroid HT so that it can be a spreader, which it is in this case, where the low conductivity direction is actually through the thickness, but because it is so thin, it acts as a nearly perfect spreader. Or if you want a very thick plate for your application, you can choose the high conductivity to be through the thickness direction. Again, you can select different materials. You can look at the performance on the right on the plot as you did before, and you can see the design performance specifically quantified in the design performance block. The biggest difference in this case is the calculations take a little bit longer, and so you'll manually press the calculate button, and you'll see a progress bar to indicate that it's doing the calculation for all of your design and design space conditions, and then it will update the plot. With that, I'm going to return to the slides. If you just bear with us for a moment. And I'll turn it back over to Bob for the conclusion.
Thank you, Dan. Thank you very much. It's been a very good collaboration with Dr. Sabatino. He also is at Easton, PA, so it makes for a very easy collaboration. It's been very productive for us here at Mintech. And to give you a summary of what we've discussed this morning before we go to the Q&A, we've introduced you or reminded you of an advanced material called Pyroid HT pyrolytic graphite. That material evidences extremely good thermal spreading due to its 1700 watts per meter K thermal conductivity. We've seen evidence of a fast and uniform thermal response. It has weight savings, and because it can be metallized, it affords the opportunity for direct solder attachment. Dr. Sabatino has explained his software modeling tool, and if any of you would like a copy of that modeling tool, There's an email that's indicated on the slide, richard.lemack@mintech.com, and we'll be able to provide that to you. If you'd like greater details on the nature of pyrolytic graphite and Pyroid HT, on our website you will find presentations and papers that I have authored or co-authored and presented at various IMAPs and MRS conferences in the past. Now, let's spend some time on the Q&A. We'll have a few minutes for questions, and if we don't get to your question, not to worry. We'll certainly post a complete Q&A transcript, including answers that we may not have time for today. It'll be posted with the webinar when it goes into on-demand mode. So at this point, I'd like to turn the program over to Richard Lemack, who will be our Q&A moderator. Richard?
Thank you, Bob and Dan. We have a few minutes for questions. Our first question is, can you review again the metallized coatings that are available on your material?
I'll take that one, Richard. Certainly. The types of metallized coatings that are available is a variety, and not only the metal itself, but also the nature in which the coating process is performed. Among the coatings that we have explored either ourselves or with customers would be a titanium, followed by a nickel chrome, followed by a gold layer, or titanium, followed by nickel, followed by gold, or titanium platinum gold. We've also provided materials which simply have either a copper or a nickel coating. We've done nickel chrome, and we've also done copper with gold. And as I mentioned before, we have the capability and facilities to explore and customize the metallized coatings for whatever your needs may be.
Bob, a second question, I'm going to paraphrase. Will this material work in a flexible monitor?
A flexible monitor. Certainly, this material has flex that could make it suitable for that application. But what I would encourage the questioner would be to provide us with some greater details of the dimensions that he has in mind, and then we can make an appropriate response. And this very often is the way we work with either customers or prospective customers, is the more details you can provide us with respect to size, thickness requirements, the better we can advise you and provide materials that meet your needs.
Are you able to make the entire heat sink out of this material?
Certainly. We have many examples where we have done just that. Again, one of the interesting things about our operation is, we're able to do, and we have expert machinists on site, and what they've been able to provide is customized materials which include the entire part or piece that is required for the customer's application.
Is this model a standalone apps or a web-based model? Dan?
It's a standalone app. So if you contact Richard through the email that was listed on the slide, he'll send you a link that will allow you to download the app directly to your machine, install it, and run it locally.
And that email again was richard.lemack at Minteq, MINTEQ.com.
Here's a question. How high an operating temperature in air will your material perform without degradation?
Good question. Certainly, because it's carbon-based, it is subject to oxidation, but temperatures below 600 degrees C would be no problem whatsoever. You know, one of the benefits of pyrolytic graphite in general is that its melting point is 3,000 degrees K. It's one of the reasons why it was used in many of the original NASA applications for the space shuttle.
Here's a question. What is the price of this material?
I guess this is, Richard, where I say I'm just a scientist, but certainly what I can tell you is, you know, one of the marketing taglines that we use is it provides diamond-like performance without the diamond-like price. And when I say not diamond-like price, I mean several orders of magnitude lower than diamond prices. But as I've been taught by our sales manager, the price, of course, is dependent on volume and the size of the material requirements. Certainly, we can provide you, when you provide us with your needs from a standpoint of volume and size, we can quickly respond with the price. But be assured, it is going to be very cost effective compared to diamond.
What is the maximum spreader dimensions available in this material?
Okay, well, we certainly have large furnaces. As I said, we're the largest global producer of high purity pyrolytic graphite. But those large plates, of course, are going to be broken down into smaller materials. So we have standardized on XY spreader dimensions at approximately 150 millimeters square maximum dimensions. If you're interested in a Z spreader orientation, we supply large dimensions, but they are made up of bonded strips. The bonds are made from high-strength carbon-based adhesive, and since those bond lines are very thin, they do not interfere with thermal performance. But here again is a case where all our responses are customized to your exact requirements. So simply give us a follow-up with your needs, and we will make a quick response, and we will jointly determine the suitability of our material for your application.
Matt wants to know how formable or machinable are the sheets of your material?
Extremely. You know, one of the benefits of this material is that in the hands of experienced machinists, it can be machined to net shape. Certainly, we have done many complicated machining parts where there are steps or chamfers, so it's quite amenable to machining.
A question that is primarily for you, Bob, or Dan, having to do with the model. What do you put in the model for the Z-axis thermal conductivity?
Well, the high thermal conductivity is 1,700 watts per meter K for the Pyroid HT. If you're referring to the flat plate model, where you have the choice of using the high thermal conductivity in the across the thickness of the plate, then that would be 1,700. But if you use the low thermal conductivity, it would be 7 watts per meter K.
key thing with the machinability of the material is that we can orient the material so that you get to choose the two directions in which the 1700 watts per meter K is acting.
A follow-up, is it possible to have a three-dimensional thermal model or thermal design?
Excellent question. The answer is yes. We had limited time today, so we didn't want to complicate things. But again, if you go back to some of the presentations on our website, we have done just that. One of the follow-ons to the case study that I showed you for the laser diode was a case study where we are able, through machining and orientation of the material, create a near isotropic system. Of course, when you do that, you have to sacrifice a bit of the average thermal conductivity, but you still can yield an average thermal conductivity of 1300 watts per meter K for the near isotropic case. So, good question, and the answer is yes.
Here's a question that involves what is the electrical conductivity of this material? And that is primarily, that information is primarily through our database and can be found on our website.
Yeah, absolutely. We have tech data sheets that would be able to give you our typical values for things like electrical conductivity and strength parameters.
Do you support mass production quantities for thin sheet heat spreader applications? And are there samples available for testing?
I think the answer is yes, but we'd have to know what you meant by what are the dimensions of your requirement. Certainly, the thickness of the application does matter for us, but give us a follow-on, and in the case of any sort of even semi-serious inquiries, create a request for quote, and we'll respond to you accordingly. But as I mentioned, we are the world's largest supplier of high-purity pyrolytic graphite, and we feel very confident that we can meet your production requirements.
How does the CTE stack up with conventional heat spreader material?
We do have that in our papers. The CTE is lower than many of the alternatives that are available. And again, if you take a look at our website, you can compare it to handbook values for copper, aluminum, etc.
James wants to know, can you create a surface by replicating a mandrel to match it?
That's an interesting question, and the answer is yes. In fact, there's another way in which you can produce not the highly oriented pyrolytic graphite, but a more standard pyrolytic graphite can be made to net shape by exactly the technique that James is suggesting, which is by using the mandrel in a male-female type relationship. We do this quite regularly.
This will be our final question. What are, again, some of the benefits of your material?
Well, if we look at the summary slide, we did review them, but I'd be happy to review them again. Number one, it's carbon, so it's lightweight. It's only 25% of the weight of copper, so that offers a design advantage. It is 4 times the thermal conductivity of copper, measured on average 1700 watts per meter K. The material can be oriented to optimize the thermal requirements of the user. The material can be metallized in a variety of metal systems that allows direct device soldering. And because of its thermal management capability, it offers a major reduction of interface temperature, junction temperature, or the ability to significantly increase the power output.
Bob, you answered that so well, we have time for just one more question.
Okay, Richard, shoot.
Can pyrolytic graphite be bonded, i.e. with graphite epoxy composite panel?
That's a little bit, not quite sure the intent of the question, but in general, yes, it can be bonded, interfaced with the more typical lower performance graphite if necessary.
Well, we're going to have to wrap up this webinar right now. Thanks to all our presenters and for spending time with us today. And thank you, our audience, for being part of this webinar event. Take care, and we'll talk to you soon.